In the next couple of lectures, we're going to develop a new technique for solving systems of linear equations based on what we did in the previous two lectures. So just to remind you, in our previous lecture, we looked at systems of linear equations and defined equivalent systems as systems that have the same solution set as the original system. And then we defined three possible ways in which you can transform a system into an equivalent system, which were swapping the order of two equations, multiplying through by something on both sides of an equation, and also adding a multiple of one equation to the other. And if you look at the example that we've got here on the right, it probably got a bit tedious, either if you were writing this yourself or you were watching me writing all these equations again and again and again. It seems like there's a lot of redundancy. It's also worth noting that it didn't really matter what we called the variables. We could have called them x1, x2, x3, x4. We could have called them x, y, z, and w. So the naming of variables played no role in our system of finding an equivalent system. And this is going to be important in what we do next, which is developing precise notation that will speed up our process of solving systems and also actually lead to greater insight into the solutions that we find when we start doing matrix algebra. So as usual, when we're developing a new area of maths, we have some definitions that we need to learn. So the first is the definition of a matrix. So a matrix has certain dimensions associated to it. It's a rectangular layout of numbers from the real numbers, having m rows and n columns. So from this you can work out if it has m rows and n columns, this means that it has m times n entries in our rectangular array. So the way we would typically write a matrix, we usually use a capital letter to name it and some square brackets to denote the matrix, and then we write our entries in. Now it's a rectangular layout. It has m rows and n columns, so same number of things in each row. So we've got, for example, 1, 3, 5 in the first row, 2, 8 minus 4 in the second row, and maybe we've got minus 8, 3, 7 in the third row. So this matrix has m is equal to 3, it has 3 rows, and it happens to have 3 columns. But m and n don't have to be the same. Things that you'll notice, sometimes people use large round brackets instead of these square things, so I could equally well have written it like this. We don't really distinguish between the two, it's really just a matter of convention. If we want to talk about a specific row of a matrix, we start by labeling rows from the top. So this would be row 1, row 2, and row 3. And if we want to reference a column, we work from left to right. So this would be column 1, column 2, and that's column 3. So this gives us also a way of indexing individual elements inside the matrix. For example, if I want to index this 1 and say which element that is, this is the element in position 1, 1, where 1 is its row and 1 is its column. So our 2 over here would be in position 2 because it's in the second row, and 1 because it's in the first column. So we can also use our A with subscripts to help us know which entry we're referring to. For example, A21 says the element of matrix A that is in the second row and first column. So that's our 2. Again, there is a notation change that happens. It doesn't really matter how you write it. I will usually not use square brackets when I'm referring to an entry, so I will usually write this just as A21 without these square brackets. And you will sometimes also see people using a lowercase a21 to represent the matrix, to represent the element. Okay, so if we have a look at this matrix over here, matrix B, well, this matrix is m by n, where m is the number of rows, so that's going to be 3, and n is the number of columns, which is 4. So we know that B has 3 times 4, which is 12 entries. And I would refer to B11 is the element in the first row, first column, so that's -1. If I wanted to index this one over here, I'd say that's B, well, let's see, it's in the second row, so that's B2, and it's in 1, 2, 3, 4, it's in the fourth column, so that's B24 is equal to 1. Okay, so now we have matrices, but we need another special kind of matrix, which is called a column vector. So a column vector of size m is an ordered list of m numbers written in order vertically, starting at the top and proceeding to the bottom. So the one thing that the textbook doesn't say, but that you could realize, is that really a column vector is an m by 1 matrix. It's just a special kind of matrix which has m rows and only 1 column. But because we end up using column vectors a lot, this is why they get their own notation. For the moment, we might even just refer to it as a vector. Now, most textbooks use boldface, lowercase letters, from near the end of the alphabet, but since it's hard to write boldface, the notation that I will use is I will put a little arrow on top. And this is also sometimes seen in textbooks. So this should have a little arrow on top. Occasionally you'll see, for example, like a little tilde underneath. It really just depends on who's doing the writing. And if we want to refer to an entry, or sometimes called a component of a vector, in the ith position, so this is really in the ith row, then again the textbook uses the notation square brackets around and subscript I, but I will sometimes just write VI, and I won't put the arrow on top to indicate I'm not talking about a vector anymore, I'm just talking about a number. So if we look at our example vector over here, we've got U1 is just 1, because we work indexing down the vector. U2 is equal to 3, and U3 is equal to -5. So this, you'll see, because this is simpler, we only have a single index for each element. This is why we think about vectors as being not exactly the same as matrices, although they are. It just helps us with the notation. We can talk about special vectors. For example, the 0 vector of size m is just a column vector of size m where every entry is 0. And in notation, we would say 0i is equal to 0 for all i's between 1 and m. So for example, here is a 0 vector, which should have zeros, not ones, and that's the 0 vector of size 2. So how does this relate to our systems of linear equations? Well, the first way it relates is we're going to create a matrix called the coefficient matrix by pulling out all the coefficients in order from our linear equations. So we pull them out, and you'll notice this was the notation that we used to define a linear system, and it was kind of clever because we can now use it straight away to pull out the coefficient matrix. So we take the coefficient of x1 in the first equation and pull it down into the first row, first column. In our first equation, the second coefficient moves into the first row, second column, and so on. So our A11 tells us that it's in the first row, first column of matrix A, but it also tells us that it was the coefficient of x1 in the first equation in our system. So what I'm saying over here is we are really using the notation that the ij entry of matrix A is aij coming from the ith equation and the jth variable. And this is pretty standard notation using these subscripts. The next thing we need to do is be able to talk about our constants in our linear equations. And as you can see, we can conveniently write the vector of constants, which is going to be a column of size m. So far we have the coefficient matrix, which is size m rows by n columns, where m is the number of equations and n is the number of variables. And now we have our vector of constants, which is a column vector of size m. And this m is the same m as we had in our coefficient matrix. The final thing we're going to do is talk about the solution vector, which is a column vector of size n, and this is important here, not m, it's n, because we want to end up with finding values for each of the variables, and we have n variables. So our solution vector is going to be it has different dimensions to our original, our vector of constants. So let's use what we've just defined in an actual system. So if we have this system of linear equations, then our coefficient matrix A is going to be equal to, now let's just check, we've got 3 equations, so it's going to be 3 rows, and we've got 1, 2, 3, 4, 5 variables, so it's going to be a 3 by 5 matrix. So I'm going to put little dots so that I make sure that I get all the entries in that I want. You don't have to do this, but I just tend to make stupid mistakes. And now I'm going to write down the coefficients. So my first row, first column coefficient is 2. Then we've got 4, minus 3, 5, and 1. Moving on to the second row, we've got 3, 1. Now notice we don't have an x3 term in the second equation, which means the coefficient of x3 is 0. Our coefficient of x4 is 1, and x5 is minus 3. And then for our final row, we've got 2, 7, minus 5, 2, 2. So this is our coefficient matrix. If we want our constant vector, that is going to be called B. And our constant vector, we just pull out the numbers on the right-hand side of our equation. So b is going to be 9, 0, minus 3. And then finally our solution vector is going to, remember, have the same number of components as there are variables, so it's going to be a length 5 column vector, and it's going to be x1, x2, x3, x4, x5. So when we've found in particular the coefficient matrix and the constant vector, this encapsulates all the important information about the system, because we don't really care what we're calling our variables. So long as we're consistent in all three equations, we could call them whatever we want. It's these coefficients and the numbers on the other side of the equal sign that are important. So we can write curly ls a b as a shorthand expression for this system of linear equations, where we know that the a is our coefficients and the b is our constant vector. And this is called the matrix representation of the linear system. So these two vectors together, these two matrices together, give us the representation. Now it's going to turn out to be useful to actually only work with a single matrix. And this leads us to define what's called the augmented matrix of a system of m equations in n variables, if it has coefficient matrix A and vector of constants B. And the way we do this is we really just add another column onto A on the right hand side, which is the column vector B. And we're going to write this as a kind of augmented. Remember, augmented means extended. We might use this line here to show that we have kind of appended our B column vector onto A. So what does it look like? Well, if we've got this matrix over here, this system of equations over here, our coefficient matrix is 1, minus 1, 2, 2, 1, 1. Be a little bit careful here. We've got coefficient of 1 for x1, 1 for x2, and 0 for x3. Our vector of constants is 1, 8, 5. And our augmented matrix is going to be 1, minus 1, 2, 2, 1, 1. So I'm copying A exactly, and now I'm just popping B in, and I use a line to differentiate where A changes into B. It's not clear at the moment why we would want to do this, but in the next lecture you'll see why it's so important.